Benjiva Pinger. Dear colleagues, I'm glad to start our today's seminar. Our speaker is Natalia Maslova, a prominent specialist in group theory from Novosibirsk. From Yekaterinburg. She is also working in Novosibirsk. And she will tell us about a very attractive part of group theory called Gruenberg-Kegel graphs, and she will tell us something beyond this topic. Let's welcome.
First of all, many thanks for inviting me. And today I will tell a few words about so-called Gruenberg-Kegel graphs or prime graphs of fine groups. My talk is dedicated to the bright memory of Professor Otto Helmut Kegel. He was a very nice person and a very nice group theorist, visited Russia for several times. He has been in Krasnoyarsk, in Novosibirsk. I have met him for several times, and really he impressed me very well. Bright memory to this person. And what about our terminology? During all my talk, a group will be finite group, and each graph will be an undirected graph without loops and multiple edges. And if I consider some object, it can be object of any nature. For example, a graph, a crystal, a dynamical system, a surface and network, anything. What do you want? Let us think about Gruenberg-Kegel graph themselves. Here, the root of this problem is the following. If you take an object and the homomorphism group of this object, usually we don't know this group a priori. So our aim is to try to construct this homomorphism group using some properties of object. For example, some properties, arithmetical properties, numerical properties, so-called, of homomorphism group of this object. For example, you consider a length of orbits, or you consider element orders, or you can consider any other arithmetical characteristics. If somebody give us these arithmetical characteristics, we need to try to understand what is this group. And it's a very good luck if this group is uniquely determined by these arithmetical characteristics. Here, if it is, it's well done. We have won, and it's perfect. Otherwise, we need to change our arithmetical parameters. For example, add some more parameters and repeat the procedure here. And the question is, what are good arithmetical parameters? And here, let us consider very well-known construction of a finite graph and try to construct its homomorphism group. In the picture, you can see this is the Peterson graph. In algebraic combinatorics, this is a very, very well-known counterexample to many conjectures. If you have a conjecture in algebraic combinatorics, first of all, you need to check this conjecture on Peterson graph. And if the conjecture is false, then with a very, very big probability, the conjecture will false on the Peterson graph. We need to construct its homomorphism group. You can see this graph has exactly 10 vertices. So this group is a subgroup of the symmetry group on 10 points. And it very well understandable that this group has so-called regular subgroup, a group of order 10. This is rotation of order 5 and inversion, which inverts inner cycle and outer cycle of this graph. So we can use the Frattini argument, and the order of this group has factorization this regular subgroup to the point stabilizer. And it's not hard to find the order of the point stabilizer. Here you can see all the calculations. I don't give more information here, but using these techniques, it's very, very easy to understand that the order of this group is exactly 120. And if you try to rotate this graph, you can easily calculate the element orders of this group. This will be exactly 1, 2, 3, 4, 5, and 6. Okay, we have some arithmetical parameters of a group. Can we find a group? Yes, the result by Rolf Brandl and Wu Zhixin. This result was obtained around 35 years ago, and it's established that if a finite group has order 120 and element orders exactly 1, 2, 3, 4, 5, and 6, then this group is exactly a symmetry group on 5 points. Okay, what do we have? We have some general problem, and we have some partial result, which occurs a tool for our solution. This is not very partial. It's a very partial case of the problem, but this group theoretical, purely group theoretical tool works in our partial problem. And then what's in the general case? If we take a set of positive integers, define the prior spectrum of this set. It's the set of all prime divisors of the integers from this set. For example, if the set is 2, 15, 21, and 35, then its prime spectrum is 2, 3, 5, and 7. And using this set, we can construct so-called prime graph of this fine set of numbers. The prime graph is a labeled graph. It's the vertices of this graph are exactly prime divisors, all the prime divisors of the numbers from the set, and two vertices are adjacent if and only if their product divides a number from the set. For example, if you consider the same set, 2, 15, 21, and 35, then its prime graph is exactly union of two cliques. One consists exactly from the vertex 2, and another is the complete graph on the vertices 3, 5, and 7. And what's about a finite group? Let's take a finite group. If the group is finite, it's easily to understand that all elements of this group have finite orders. What is the order of an element? It's the smallest number such that this element in this power gives identity of the group. So in finite group, each element has prime order. And the spectrum of a finite group is the set of all element orders of this group. And the prime spectrum of a finite group is the following number. There are some equivalent definitions of this number. The set of all prime divisors of the order of this group. Equivalently, the set of all prime elements from the spectrum. Equivalently, the set of all prime divisors of the elements from the spectrum. You can easily prove that all these definitions are equivalent for a finite group. And a prime graph of a finite group, or Gruenberg-Kegel graph, or GK graph, like Peter Cameron likes to name this graph, is the following graph. The vertices of this graph are the prime divisors of the order of a group, so-called prime spectrum of a group, and two vertices are adjacent if and only if the product is an element order of this group. Here, in the definition of the prime group of a prime graph of a finite set of integers, you can see that if you take a set and close this set with respect to taking divisors, then the graph is stable under this operation. And for a affine group, it's very easy to find that its spectrum is closed under taking divisors. So you can define the Gruenberg-Kegel graph like a prime graph on the set of element orders of this group. And a very easy exercise, two primes are adjacent in the Gruenberg-Kegel graph of a affine group. If and only if there are elements of such orders in the group which commute. If the graph is disconnected, then take a group G. If gamma of G is disconnected by S at G, we denote the number of connected components on this graph, and by pi 1, pi 2, and so on, pi s of G, we denote these connected components. And if our group has even order, we assume that the first component is the component which contains 2. Okay, what about history? The concept of the Gruenberg-Kegel graph appeared in unpublished manuscript by Carl Gruenberg and Dr. Kegel, and this concept has received the almost immediate application. Almost immediately, the concept has received an application. The augmentation ideal of an integral group ring is decomposable as a model if and only if the Gruenberg-Kegel graph of this group is disconnected. It's almost immediate. It was received almost immediately after the concept of Gruenberg-Kegel graph was defined, and the Gruenberg-Kegel theorem was also proved in unpublished manuscript by Carl Gruenberg and Dr. Kegel, but it was published only by Williams 6 8 later. Williams is one of students by Carl Gruenberg. And let us give some examples. There are non-isomorphic groups with the same spectra. For example, symmetry groups on 5 and on 6 points. There are groups with different spectra, but with the same Gruenberg-Kegel graph. For example, alternating groups on 5 and on 6 points. Moreover, if you take the alternating group on 5 points, then the group is uniquely determined by its spectrum. However, the alternating group on 6 points is not uniquely determined by its spectrum, and both are not uniquely determined by the Gruenberg-Kegel graph. There are groups which have Gruenberg-Kegel graphs which are isomorphic as unlabeled graphs, but not equal like labeled graphs. For example, if you consider the alternating group on 10 points and the orthomorphism group of the second Janka group, then the Gruenberg-Kegel graphs are isomorphic like unlabeled graphs. The prime spectra of these groups coincide. However, the labeled graphs are distinct. And about recognition problem, what is the aim of our research? The aim of our research is to construct some techniques which allows us to recognize a group with its arithmetical parameters. For example, with Gruenberg-Kegel graph. So a group is recognizable by spectrum or by Gruenberg-Kegel graph respectively if this group is uniquely determined by this arithmetical parameter up to isomorphism. Is K recognizable by the arithmetical parameter if there are exactly K pairwise non-isomorphic find groups with this arithmetical parameter. Almost recognizable if it's K recognizable for some positive integer K, and affine group is unrecognizable by some arithmetical parameter if there are infinitely many pairwise non-isomorphic groups with this arithmetical parameter. For example, there are infinitely many groups such that they are pairwise not isomorphic, and their spectra coincide with spectrum of our group, or there are infinitely many pairwise non-isomorphic fine groups such that their Gruenberg-Kegel graphs coincide with the Gruenberg-Kegel graph of our group. What's about recognition by spectrum? A very nice criterion on recognition by spectrum was obtained by Viktor Mazurov and Woodrow Shim more than 13 years ago. A affine group is unrecognizable by its spectrum if and only if there exists a affine group with non-trivial solvable radicals such that spectra of this group and of our group coincide. What does it mean that the solvable radical of a affine group is non-trivial? It's equivalent to the statement that this group has a non-trivial normal abelian subgroup. So, as a corollary of this result, we obtain that if a affine group is recognizable by spectrum, or even almost recognizable by spectrum, then the solvable radical of this group is trivial. And the question on recognition by spectrum is interesting only for groups with trivial solvable radical, and especially for fine simple groups. Let us remind what are the fine simple groups. The term simple group in group theory is almost the same that the term prime number in the number theory. Fine simple groups were classified. Here, it's some joke. There is the periodic table of fine simple groups. Of course, this table is infinite. It's not finite, but you can imagine that there exists some table in which all the fine simple groups were presented. Let us discuss the details. A non-trivial group is simple if it doesn't contain non-trivial proper normal subgroups. As I have mentioned, fine simple groups were classified, and each fine simple group is either abelian and then this group has prime order, or is non-abelian and then this group is contained in the following list: alternating groups of degree at least 5, 6 series of classical groups. These are well-defined subgroups of GL and Q, matrix groups of degree n over a finite field of order Q. So-called exceptional groups of Lie type, there are 10 series of such groups and 26 sporadic groups. Here you can see there are all the sporadic groups. And
first, what is so-called? What is so-called?
I will remind. Don't
Yes,
worry.
and also по-русски, как?
I will remind.
And also, are almost simple groups classified?
And yes, of course, a fine group is almost simple if this group is between a fine simple group and the homomorphism group of this group. And in this case, this simple group is called by the so-called of this almost simple group. And of course, fine almost simple groups were classified. Moreover, if you take a fine simple group, then a corollary of classification of fine simple group, then the factor group of the full homomorphism group by the inner homomorphism group of a fine simple group is always solvable. It's so-called Schreier conjecture, really the Schreier theorem, but historically it's called the Schreier conjecture. This theorem is a corollary of the classification of fine simple groups. So Here you need to remember affine simple group is almost the same like the prime number, a prime number in the number theory, and affine group is almost simple if it's between affine simple group and its homomorphism group. And all these groups were classified. And what about recognition by spectrum? Almost all fine simple groups are almost recognizable by spectrum. Moreover, each fine simple group is uniquely determined by the pair of parameters spectrum, the spectrum and the order. So it's exactly the situation then. The spectrum is not enough, but if we add the order, then this pair of parameters uniquely determines the group. And there are almost simple groups which are recognizable by spectrum, almost simple but not simple. There are examples of groups, if you see here, with trivial soluble radicals, but with non-simple circles, which are recognizable by spectrum. And very strong result by Yan, Gorshkov, Staroletov, and Vasilyev that for each natural number k, there exists a fine simple group G depending on k such the direct product of k copies of this group is still recognizable by spectrum. It's a very, very nice result, I think. And what's about recognition by Gruenberg-Kegel graph? We were very lucky to prove that almost the same follows for Gruenberg-Kegel graphs. A fine group is unrecognizable by Gruenberg-Kegel graph if and only if there exists a fine group with non-trivial soluble radical and the same Gruenberg-Kegel graph as our group. Of course, from 2 to 1, it follows from Mazurov-Schitt theorem. But from 1 to 2, this is rather tricky and nice proof. And let us consider some corollaries of this result. In contrast to recognition by spectrum, where groups with non-simple circle can be recognizable, we have proved that if a group is almost recognizable by Gruenberg-Kegel graph, then this group is almost simple. Each group with the same Gruenberg-Kegel graph is also almost simple. The number 2 is non-adjacent to at least odd prime, at least one odd prime in the graph. And the group contains at least 3 pairwise non-adjacent vertices. As a corollary, a fine group is almost recognizable by Gruenberg-Kegel graph if and only if each group with the same Gruenberg-Kegel graph is almost simple. And why is it interesting to consider almost simple groups? Probably it's a very small class of groups and it's not interesting. It's not right. If we take an object and the homomorphism group of this object, and if we want to look to this group, what can we do? First of all, we can consider the orbits of this group. And then the homomorphism group is the subdirect product of symmetry groups, of projections to components, so-called projections to components. In any case, it's a subgroup of the direct product of corresponding symmetry groups of the orbits. So we can restrict the group option to each orbit and consider only the cases then the group is transitive. Secondary, we can try to consider the blocks. What are the blocks? Which are sets such that the block and the image of this block under the group action either have empty intersection or coincide. And if we consider maximal blocks, then on the set of blocks, the action is so-called primitive. doesn't have proper blocks. And primitive permutation groups were classified. It's so-called Onen-Scott theorem, proved for primitive permutation groups by Martin Liebig, Cheryl Prager, and Jan Saxel in 1989. And each primitive permutation group is either has very well almost geometrical description or is almost simple. And in the first 7 cases, we know many details of actions. And in the last case, we know only the structure of the group. So exactly almost
And
simple
what is a
groups.
holomorph? What is a holomorph of an abelian group?
It's special kind of primitive permutation group. Like you consider abelian group and special action of homomorphism group. As an example, like affine group. Affine group. All these special cases of actions were well described. And in the last case, almost simple groups, they are not well described themselves. They just known to be almost simple, like group theoretical structure. So, in some sense, it's the hardest one case. What is the main idea of all this situation? Almost all fine simple groups are almost recognizable by spectrum, and there are many non-simple groups which are recognizable. And if a group is recognizable by Gruenberg-Kegel graph, then the group is recognizable by spectrum. However, computing the spectrum of a group is not
Is it
easy.
obvious from the definition?
Sorry?
Is it obvious from the definition that if it's recognized?
Yes. It's obvious from definition. The spectrum defines the Gruenberg-Kegel graph. So if a group is uniquely determined by Gruenberg-Kegel graph, it's easy to understand that it's uniquely determined by spectrum. However, computing on the spectrum is not easy. And if you remember the exercise from one of the first slides, computing the Gruenberg-Kegel graph of a group is much more easier. And if a group is almost recognizable by a Gruenberg-Kegel graph, then the group is almost simple. However, the class of almost simple groups plays keynote role in the study of primitive permutation groups due to the Onen-Scott theorem. So this is a very interesting class of groups, and it's interesting to understand are they recognizable or not by Gruenberg-Kegel graph. Moreover, recognition by Gruenberg-Kegel graphs gives us a very powerful tool in some cases. For example, if you consider the monster group, it's a huge fine simple group, a huge group of order H0H power 10 to 10 power 53. You can consider the order of this group. However, the group is huge, but the graph is visible on the slide. There are exactly 15 vertices, and you can draw this group. And a very amazing fact that this group is uniquely determined by its Gruenberg-Kegel graph. So, if you need to send the information about this huge group to another galaxy, you need to define, to give a definition of fine group, to definition the order of a group, the order of an element, to define the Gruenberg-Kegel graph, to draw this picture and send. And the next message will be develop your group theory, and no else. You will send all the information about the monster group. In the contrast of this, about small groups, if you find simple groups such that their order divides only to small primes, at most 15, or at most 13, then there are exactly 55 such groups. And if you consider recognition by spectrum, but then the most part of them are recognizable. And in the same time, only 5 of them are recognizable by Gruenberg-Kegel graph, and 58 are unrecognizable. So for small groups, this tool doesn't work well in some sense. However, 5 are still recognizable, and they can use this information, for example, as a tool for another research to define some group actions and so on. So they have a general problem. If we take a find almost simple group, decide whether this group is recognizable or almost recognizable or unrecognizable by its Gruenberg-Kegel graph. On the slides, you can see 2 papers in which you can find a survey of some known results. One of them belongs to me and Peter Cameron. Another is a survey paper in the proceedings of the World Meeting for Women in Mathematics, which took place 4 years ago. And one more associated problem to problem 1. Describe almost simple groups such that in the Gruenberg-Kegel graphs of these groups, 2 is non-adjacent to at least 1 odd prime, and the graph contains at least 3 pairwise non-adjacent vertices. The recognition problem is much more easier for the case then the graph of a group is disconnected due to the Gruenberg-Kegel field.
Can you please remind what a Frobenius group is?
A Frobenius group is a find group such that this group contains a proper subgroup such that if you take each element from the group but not from the subgroup and conjugate this subgroup by this element, then the intersection of the group and the conjugate is trivial, is equal to 1 for each element not from the subgroup. So, as an example, if you consider a find field and its additive and its multiplicative group, and if you take a natural action of multiplicative group of a find field to additive group, if you consider the natural semi-direct product, then it will be a Frobenius group, and a subgroup will be equal to this multiplicative group of a field, which acts on an additive group. A 2 Frobenius group is a group which was made from 2 different Frobenius groups. And it's not very important for general understanding. These are rather easy cases in some sense to consider in sense of recognition, since each Frobenius group has non-trivial solvable radical, and each 2 Frobenius group has non-trivial solvable radical. So if we consider a group with disconnected Gruenberg-Kegel graph and find that the graph of this group coincides with the graph of some Frobenius group or 2 Frobenius group, then we can easily prove that the group is unrecognizable. And the third possible case is an extension of some nilpotent group by some almost simple group, also with disconnected Gruenberg-Kegel graph. And due to this result, the recognition question by Gruenberg-Kegel graph is much more easy for the groups than which have disconnected graphs. About some recent results in this area. Around 20 years ago, Viktor Mazurov has conjectured that each fine simple group such that its Gruenberg-Kegel graph has at least 3 connected components, then this group is recognizable by spectrum. This conjecture is true, and the final step in the proof of this conjecture was made by Anatoly Kondratiev around 10 years ago. Moreover, for all fine simple groups with disconnected Gruenberg-Kegel graphs, the question of recognition by spectrum is solved. This result belongs to many authors, and the final step was made by Viktor Panshin. He is a PhD student from Novosibirsk. A preprint of this paper is now on arXiv. You can easily find it. Here, a partial case of our general problem 1. If we take a simple group with at least 3 connected components of Gruenberg-Kegel graph, or disconnected Gruenberg-Kegel graph, then define, is this group recognizable, almost recognizable, or unrecognizable by Gruenberg-Kegel graph. For the case of disconnected Gruenberg-Kegel graph, as I have mentioned, the problem is much more easy than for the case of connected graphs. And groups with at least 3 connected components of Gruenberg-Kegel graphs are known. And for some of them, the question was solved or solved partially. And for exceptional groups of Lie type, the question was not solved in the general case. And a fine group is quasi-recognizable by spectrum, by Gruenberg-Kegel graph, if each group with this parameter has a unique non-abelian composition factor, which is isomorphic to our group. You don't need to keep in mind this definition, just for the general information. Here, there are some results for groups with disconnected Gruenberg-Kegel graphs. I just rotate the slides. You can see that there are some results, some partial results, and me and Viktor Panshin, who was mentioned several minutes ago, and Alexey Staroletov, he is also from Novosibirsk, we have proved that if we take an exceptional group of Lie type with at least 3 connected components of its Gruenberg-Kegel graph, then, except of the case of Suzuki groups and G2-3, this group is almost recognizable by Gruenberg-Kegel graph. And mentioned Suzuki groups and G2-3 are unrecognizable. And also, we have obtained the results for E6Q and twice E6Q. These are exceptional groups of Lie type with exactly 2 connected components of Gruenberg-Kegel graphs. These groups are also almost recognizable. And recently, me and Viktor Panshin proved for the groups F for Q, where Q is odd and equals to 0 or plus minus 2 modulo 5, that these groups are almost recognizable by Gruenberg-Kegel graph. What about the case of connected Gruenberg-Kegel graph? There is a strong generalization of the Gruenberg-Kegel theorem, which established that if we take a non-solvable group such that 2 is non-adjacent to at least 1 odd prime on the Gruenberg-Kegel graph of this group, then there is a non-abelian simple group such that the factor group of our group by its solvable radical, not nilpotent radical, but solvable radical, is almost simple with circle S. And there are some extra conditions. And a very important feature, as a corollary of this result, a very important feature of Gruenberg-Kegel graph of each fine group is that in Gruenberg-Kegel graph of each fine group, the set of vertices which are non-adjacent to the number 2 is a union of cliques. It's a very strong combinatorial property of the class of all Gruenberg-Kegel graphs of find groups. Okay, if you forget about the group theoretical structure, and if you take Gruenberg-Kegel graph like some labeled graph, just graph with labeling, a simple graph is a labeled graph if its vertices are labeled by pairwise distinct primes. And we have proved that for a labeled graph, me and Peter Cameron, we have constructed a polynomial function of degree 7 such that for each labeled graph, there are infinitely many find groups such that the Gruenberg-Kegel graphs are equal to this graph, if and only if there are more than the value of function of on the number of vertices of this graph, groups such that the Gruenberg-Kegel graph coincide with our given graph. So, for a given graph, you can understand, is the number of groups with this graph finite or infinite? If there is a number of groups more than given number, such that the Gruenberg-Kegel graphs coincide with this graph, then we know in advance that the number of groups with this Gruenberg-Kegel graph is infinite. We can, of course, the bound can be improved. And Maria Grichkoseyeva and Andrei Vasilyev have improved this bound. They have constructed a polynomial function of degree at most 5. However, due to result by Andrei Zavarnitsyn, this function cannot be a constant. So it's at least of degree 1. However, such a function exists and is polynomial. And for find simple groups, what does it mean? It means that the number of pairwise non-isomorphic almost simple groups with pairwise coinciding Gruenberg-Kegel graphs is bounded by this function on the number of vertices of the graph. And if we omit the statement that group is almost simple and restrict this statement to simple groups, then we have the conjecture by Andrei Vasilyev. Andrei Vasilyev has conjectured that there are at most 4 pairwise non-isomorphic find simple groups with pairwise coinciding Gruenberg-Kegel graphs. This research was investigated by Mina Hagi, Maria Zvezdina, and Marianna Zinovьева. I hope next week Marianna Zinovьева will give more details about this research area. I will not tell more now since it's her research. And about recognition by isomorphism type of Gruenberg-Kegel graph. Of course, now we looked to a group and this Gruenberg-Kegel graph. We looked to Gruenberg-Kegel graph like to labeled graph. And now let us imagine that we have deleted all the labels. And a find group is recognizable by isomorphism type of its Gruenberg-Kegel graph if for each find group, Gruenberg-Kegel graphs of groups G and H are isomorphic as unlabeled graphs if and only if the groups are isomorphic. So you can remember that if a find group is recognizable by Gruenberg-Kegel graph, then this group is almost simple. Of course, if a find group is recognizable by isomorphism type of its Gruenberg-Kegel graph, it's forced to be recognizable by Gruenberg-Kegel graph. This implies that each group which is recognizable by isomorphism type of its Gruenberg-Kegel graph is almost simple. And here we have another problem. Take almost simple groups and decide whenever they are recognizable or almost recognizable or unrecognizable by isomorphism types of the Gruenberg-Kegel graphs. There are no many results in this direction. The first result in this was obtained by Andrei Zavornitsyn 20 years ago. He has proved that the fourth Yanka sporadic simple group is the unique finite group with exactly 6 connected components of its Gruenberg-Kegel graph. And as a corollary, this group is uniquely determined by isomorphism of its Gruenberg-Kegel graph. Another 2 examples were constructed by me and Peter Cameron around 3 years ago. They have proved that exceptional groups of Lie type G2, 2G227 and EH2 are recognizable by isomorphism types of the Gruenberg-Kegel graphs. And a recent paper, this paper was recently published in Journal of Group Theory by Tom Popil and Melissa Lee. They completed the solution of recognition question by isomorphism type of Gruenberg-Kegel graph.
And who proved the theorem about the monster group?
Monster is recognizable by isomorphism type of its Gruenberg.
Who proved it?
Yes, a monster is recognizable.
Yes, and I asked who proved it, who recognized it?
By isomorphism type, Tom Popil and Melissa Lee. All the finite simple sporadic groups will the solution of this question was completed by Tom Popil and Melissa Lee. This monster is recognizable even by isomorphism type of its Gruenberg-Kegel graph. I'm sorry, I will use my slides. If you take the monster group and even if you delete labelings and send to another galaxy the shape of Gruenberg-Kegel graph, it will still uniquely determine the monster group. Very strong information about a finite group. Monster is uniquely determined by isomorphism type of its Gruenberg-Kegel graph. And our recent result with Minzhuchenya Marianna Zinovieva, if you consider twice E62 and EHQ for Q 3, 4, 5, 7, 8, 9, and 17, then these groups are also uniquely determined by the Gruenberg-Kegel graphs. If you consider the group twice E62, its graph is presented in the picture. You consider it's rather small and nice graph, and this graph uniquely determines the group. Here we have another problems is an almost simple but not simple group which is recognizable by the isomorphism type of its Gruenberg-Kegel graph. There are still no known examples of such almost simple groups. And is the number of groups which are recognizable by the isomorphism type of the Gruenberg-Kegel graphs finite or infinite? Both these questions are in the Kaurovka notebook, in the fresh version of the Kaurovka notebook published last month. And about graphs defined on groups and their connection to Gruenberg-Kegel graph. And now I will give some brief excursion to this research area without important details, just mention some results. We can define a graph on the set of elements of a group. The graph is a commuting graph if the vertices are adjacent if and only if they commute in the group. A power graph, this is unlabeled graph two vertices are adjacent if and only if one of them is a power of another. Enhanced power graph. If the group generated by this pair of elements is cyclic. And deep commuting graph. If the inverse image of G and H compute in each central extension of this group. So there are some kinds of graphs defined on the set of elements of a group. And I remind that a graph is a cograph if it can be built from one vertex graph by the operations of disjoint union and taking a complement. And it's well known that a graph is a cograph if and only if it forbids a chain of length 4. There are no indexed subgraphs which are chains of length 4. Here there is an example of the very, very strong impact of...
Excuse me, you asked whether the number of graphs which are recognizable by the type of the Gruenberg-Kegel, is it finite or infinite?
Yes,
But
yes, yes.
if we label the Gruenberg-Kegel...
There are infinite series which are recognizable by labeled graphs. There are examples. For example, almost all the exceptional groups of Lie type, E6Q and twice E6Q, they are almost recognizable, but we can easily construct a subseries which are recognizable. And in the survey, there are infinite series which are recognizable. For example, here, the orthogonal groups. By labeled graphs, there are infinite series of groups which are recognizable. But if we delete labelings, it will be a more strong condition. So it's unknown is the number of groups which are recognizable by an unlabeled graph find on infinite. Even this is unknown. Okay. Here, this theorem is an example that the properties of commuting graphs have very strong impact to the group theoretical structure. For example, if the commuting graph of a group is a cograph, then this group is very, very close to solvable. Either have properties of solvable graphs or have exactly one non-abelian composition factor. In each case, it's very close to a solvable group. Moreover, if power graphs or commuting graphs or enhanced power graphs or diff commuting graphs of two groups are isomorphic, then Gruenberg-Kegel graphs of these groups as labeled graphs coincide. Moreover, if you take a finite group, then the enhanced power graph of this group is equal to the power graph if and only if Gruenberg-Kegel graph doesn't have edges. If and only if G is a known group, we can explicitly give an explicit list of such groups. Here you can see that the properties of graphs defined on groups are very close connected to the properties of its Gruenberg-Kegel graph. Moreover, there is another project by me and Andrea Lucchini and Norva Sotman, which where we work with subnormal graph of a finite group. It's directed graph. And we have proved that the investigation of subnormal graph of a finite group can be reduced in some case to the prime fitting graph of this group, very close to Gruenberg-Kegel graph. Now, I will not give more information here. Let us tell a few words about combinatorial properties of Gruenberg-Kegel graphs of affine group. Due to the result by Maria Silva Lucidon, if Gruenberg-Kegel graph of a affine group has an industry clique, then the group is non-solvable. And around 10 years ago, a group of American mathematicians, Alexander Gruber, Thomas Keller, Mark Lewis, Kelly Norton, and Benjamin Strasser proved that if we take a simple graph, then this graph is isomorphic to the Gruenberg-Kegel graph of a solvable group, if and only if the complement to this graph is free colorable and triangle free. And I have wrote to Kaurovka notebook problem. Is the non-solvable group such that this group, the graph of this group has free cliques, but is not isomorphic to the Gruenberg-Kegel graph of each solvable group. It means that the complement is not free colorable. And if there exists an example of such group, then this example cannot be an almost simple group, as me and Ilya Gorshkov proved. Now, by the Fate-Thompson theorem, each group of odd order is solvable. Therefore, if G is a group of odd order, then the complement of its Gruenberg-Kegel graph is free colorable and triangle free. And me and Minju Chen and Ilya Gorshkov and Nanin Yang proved that if a group has even order and there are vertices which are non-adjacent to 2 in the Gruenberg-Kegel graph of this group, then the set of all the vertices which are non-adjacent to 2 is a union of cliques. It's a very, very strong combinatorial property. And using this property, we can describe Gruenberg-Kegel graphs which are strongly regular, or strongly regular graphs which are Gruenberg-Kegel graphs of affine groups. Remind that a graph is k-regular if each vertex of this graph has degree k. A graph is strongly regular with parameters v, k, lambda, and mu if this graph has exactly the vertices, is regular of degree k, each pair of adjacent vertices has exactly lambda common neighbors, and each pair of non-adjacent vertices has exactly mu common neighbors. And around 10 years ago, Jack Cullen, in private communication with me, asked, what are strongly regular graphs which are isomorphic to Gruenberg-Kegel graphs of affine groups? Why is this case interesting? Really strongly regular graphs have very, very strong impact to many areas of mathematics. Coding theory, group theory, geometry, lattice theory, and so on. And to find some construction of a strongly regular graph, like Gruenberg-Kegel graph of some group, is a new development of the theory of strongly regular graph in some sense. And using the results about vertices which are non-adjacent to two in Gruenberg-Kegel graphs of affine groups, we have proved that if a strongly regular graph is isomorphic to Gruenberg-Kegel graph of a affine group, then either this graph is the complement to a triangle-free strongly regular graph, or is a complete multipartite graph, or this graph is a complete multipartite graph with all the parts of type 2. Moreover, in the case 2, each such a graph is realizable as Gruenberg-Kegel graph of a affine group. There is a construction. However, for triangle-free strongly regular graph, now it can occur that there are no groups with such Gruenberg-Kegel graphs. So a partial case of problem H is a strong...
When you say complement, do you mean the complement in the complete graph?
The complement of complete graph is an empty graph.
No, I mean the complement to gamma. Where the complement? In the complete graph.
What is the complement of a graph? You take edges and take non-edges. And in the complement graph, two vertices are adjacent if and only if they are non-adjacent to our graph.
Okay.
So we have a partial case of problem 8. Is there a strongly regular graph such that this graph is triangle-free and is not free-colorable, and the complement of this graph is isomorphic to the Gruenberg-Kegel graph of a non-solvable group? If this question is still open. Just two remarks. A theorem about strongly regular graphs forces us to consider the cases of complete multipartite graphs, which are Gruenberg-Kegel graphs of fine groups. And we considered these graphs initially with Dusan-Pagon. We considered complete bipartite graphs, which are Gruenberg-Kegel graphs of fine groups. And in the paper with Minju Chen, Ilya Gashkov, and Yin Yan, we were forced to consider complete multipartite graphs with each part at least 3. And we have proved that these graphs are never Gruenberg-Kegel graphs of fine groups. And for complete bipartite graphs, we have obtained a complete classification with Dusan-Pagon. So here there are some references which can be found. And let me remind, I'm chairing the Ural Seminar on Group Theory and Combinatorics. This seminar works every other Tuesday, usually 4 p.m. by Yekaterinburg, purely online. There is a reference to the seminar website. To attend seminar meetings, it's necessary to register on the seminar website and nothing else. And you are very welcome. And thank you for your attention.
Okay, thank you very much for the talk. Actually, we have a project seminar friendship, and we have some. So we are friends with this seminar, and actually we have other projects like. So we upload our talks to YouTube and so do many other things. Which unite people and ideas. Are there any questions? Or comments?
Everybody is very welcome to write me by email if you want to.
Yes, sure. Actually, there was a beautiful course on group theory by Richard Borcherds. He had lots of talks about the monster group. So there was a monstrous moonshine conjecture. Do you have any relations with the Borcherds school?
At that moment, still no, but mathematics is infinite and amazing. Probably there are some connections. Probably we just don't know about these connections.
Okay. Are there any further questions? Okay, so if it's not the case, so let's thank the speaker again for a wonderful talk. So that's all for today.
Thank you for inviting me.
Okay, thank you.